So a natural question is, well, if we know what the sum of the measures of the angles are in a triangle, well, what is the sum of the measures of the angles in any other polygon? So we're going to show a little formula and some reasoning behind that formula, but we're going to limit ourselves just to these convex polygons because the argument for convex polygons is a little easier than it is for ones that aren't convex. And what do I mean by a convex polygon? Well, it's a polygon where every line segment joining two vertices is in the interior of the polygon. You can think it has no kind of bend ends. What do I mean by that? Well, let me show you. Here is a convex polygon here, and you can see that any line segment that I draw joining two vertices, here's one here, that lies in the interior. And this happens for every single pair of vertices that I connect. You can see that I'll just do them all, why not? You can see that every line segment that I draw is in the interior. It's contained in the interior. What ones am I missing? And this one, I think that's all of them, or close to all of them, but you get the idea. Oh, we're missing one more. There it is. That's all of them. But this example here, we have this little nook here you can think of. And this is a non-convex polygon because here is one line segment that's joining two vertices that is outside my polygon. So it's not in the interior. So this is non-convex. But, and we won't get into the particulars of this, but you can always split a non-convex polygon into a bunch of convex polygons. And if you do that, here's two convex polygons. You can kind of modify the argument we're going to make to work for every type of polygon. But just in the interests of kind of simplicity, we're just going to concern ourselves with convex polygons. So here is our theorem. Let me tell you what it says. It says, if you have an N-Gon, then the sum of the measures of the angles is n minus 2 times 180. And you can kind of see what the argument is going to be for this formula just in the formula itself. We know there are 180 degrees inside every triangle, or I should say the sum of the measures of the angles is 180 degrees. So what we're going to do is we're going to split our N-Gon into n minus 2 triangles. And then the sum of those angles by postulate 6, our angle addition postulate, that's going to give us this n minus 2 times 180. So let's write this up. So here's a little proof. And I want to make a note here before we do this that we restrict our argument to convex N-Gons, but this can be modified without too much difficulty, but it's kind of, there's a lot of bookkeeping to take care of that. I don't want to show you guys, but the argument can be modified for non-convex as well. Okay, so let's consider and convex, maybe I'll say a convex N-Gon. And I'll just draw a typical N-Gon over here in blue. We'll have it have 1, 2, 3, 4, 5, 6, 7, 8 sides So this is an octagon. It's regular-ish, although all the sides aren't particularly the same length. But whatever, it is an N-Gon. Okay, and in this case, n is 8. But this argument works for any convex N-Gon that you like. Now, choose any vertex and draw a line segment from that vertex to all other, and let's say non-adjacent vertices. And the reason I said non-adjacent, because let's say we pick, this is our chosen vertex, doesn't matter which one you choose, just choose one of them. These two are the adjacent vertices, and there's already a line segment connecting them, so I am not going to deal with them, just the non-adjacent ones. So I am going to draw a line segment from every non-adjacent vertex to our chosen vertex here. And what does that do? Well, that breaks up our N-Gon into, well, if we think about it, n-2 triangles. Here we drew 5 line segments, 3, 4, 5, which broke up our interior into 6 regions. If you draw 5 line segments coming from the same point in a region, it'll break it up into 6 parts. If you draw n line segments, it'll break it up into n+1 parts. And each of these parts is indeed a triangle. So in this case, we broke up our N-Gon, we drew 5 lines, and we broke it up into 6 triangles. So in general, we break up our N-Gon into n-2 triangles. So this divides our N-Gon into n-2 triangles. By the previous theorem, remember the previous theorem said that a triangle has an angle sum of 180 degrees. A triangle has, I'll just scroll down here a little bit, an angle sum of 180 degrees. So by postulate 6, which says, well, the measure of, say, this angle here is going to be the sum of those guys. Well, all of the angles of the triangles, every single angle, is part of an angle of our N-Gon. So if we add all the angles of the parts of the triangles, we get the entire sum of the angles of our N-Gon. So by postulate 6, our N-Gon has an angle sum of n-2 times 180 degrees. And that is that result. So that's fantastic. Let's do an example. All right, so let's find the sum of the measures of the angles of a 12-gon, or if you like, a dodecagon. Okay, so we know that the sum of the angles, or let's say angle sum, that's probably a little shorter to write, the angle sum is going to be n minus 2 times 180 degrees, which is, well, we know n in this case, it's an N-Gon, which is 12 in this case. So we have 12 minus 2 times 180 degrees, and 12 minus 2 is 10, and 10 times 180 is 1,800 degrees. So the sum of the angles of a 12-gon is 1,800 degrees. Well, let's do another example. Is there an N-Gon with an angle sum of, let's say, 2,100 degrees? Okay. Well, let's check. Maybe a good idea here, pause the video, see if you can figure out how to solve this problem. Okay, now that you're back, well, now we have the angle sum, and we want to solve for n. And kind of a realization here, this is the important bit, realization, is that n must be, in fact, maybe I'll write it as this, it must be a natural number or a counting number, and n has to be greater than or equal to 3. You can't make a polygon with less than 3 sides. So we know that if this is true, if there is an angle polygon with an angle sum of 2,100 degrees, we know that n has to be some natural number greater than or equal to 3. Okay, so let's see if this is true. So the angle sum is 2,100, and that equals n minus 2 times 180. So let's solve for let's simplify this. So 2,100 equals, let's expand this out, and our 180 times n is 180n, and 2 times 180 is 360. Okay, we want to solve for n, so let's subtract 360, add 360 to both sides. And we get that 2,460 degrees equals 180 times n. And just to make my life a little bit easier, because I see this, I'm going to divide both sides by 10, since they both have a factor of 10. It just makes my life a little easier. You don't have to do this. You could go straight to dividing by 180. But I see this as 246 degrees equals 18 degrees times n. Now, we could simplify this even more. In fact, why not? I see a common factor of 6 here. So 246 has a common factor of 6. It's divisible by 2 for sure, since 6 is divisible by 2. And it's divisible by 3, since 2 plus 4 plus 6 is 12, and 12 is divisible by 3. 18 is definitely divisible by 6. 6 times 3 is 18. So let's divide by 6 as well, just to make our life a little easier. Again, you don't have to do this. You could divide by 18 at this point with some long division if you wanted to. And 246 divided by 6, you can check. This is going to be 41 equals 3n. Now it's clear to see that if we divide both sides by 3, well, 41 divided by 3 isn't going to be a whole number. 3 divided by 41 gives you, what is that going to be? That is going to be 13 with a remainder of 2. So n is going to be 13 and 2/3. But remember, we can't have a 13 and 2/3 Gon. It doesn't make sense to have 2/3 of a size. So that means, since n isn't a natural number, there is no N-Gon with angle sum 2,100 degrees. Okay, let's talk about a regular N-Gon. So, a regular polygon is a very, very symmetric polygon. And the two things that make it incredibly symmetric are that all angles are congruent, so they all have the same measure, and all sides are congruent, so they all have the same length. So let's draw a couple just to see what's going on. And we know a few of these, of course. So the typical one in 3 dimensions, in fact it's the only one, is your equilateral triangle. All sides are the same length. And indeed, all angles are congruent. Okay, now let's do in 4 dimensions. Well, we want all sides to be the same length, and all angles are the same angle. So that's your square, and then you're going to have a regular, say, pentagon. I'm going to do my best to draw this. That's not bad, but I'll just put in some markings to kind of fudge it. So all of these angles are congruent. And let's do one more. How about the octagon? So let me try and draw this. Let's try here, here, here. Not perfect, but it will do. And again, it doesn't matter if you're a good drawer or not. You can just fudge it by putting markings in. So every side is the same length. Look at that. And every angle is the same measure. So even if you're not a good drawer like me, you can fudge it just by putting in some angle markings. Now there are some examples. Let's do some non-examples, and I'll just do it in quadrilaterals. So let's talk about a figure where all angles are congruent, but not all sides. And we know what that is. That is a rectangle. So here, we have all angles are congruent, so that's satisfied. They're all 90 degrees. But all sides aren't congruent. The top is congruent to the bottom, but the left side and the right side are congruent to each other, but not the top and bottom. Or, well, how about one where the sides are the same length, but the angles aren't congruent? So a rhombus. Every side is the same length. It's like a shifted square. But these two angles, the opposite ones, are congruent, but not congruent to the adjacent ones. So there's 2 non-examples. Okay, so let's see if we can come up with a formula for, well, if we have, say, an octagon, what's the measure of one angle in, say, an octagon, or in general, any N-Gon? Remember, we know the sum of the angles in any N-Gon. We worked that out in the last slide. But can we use that to determine the measure of one angle of a regular N-Gon? So pause the video now, see if you can figure it out. Okay, so the measure of one angle in a regular N-Gon is the following. Well, we know the sum is n minus 2 times 180. And we have to divide that angle sum into equal parts. How many equal parts? N equal parts. If we have an 8-gon, an octagon, there are 8 angles that have the same measure. So we need to divide that 6 times 180 into 8 equal parts. So we need to divide, in this case, by n. So there's our formula for the measure of one angle in a regular N-Gon. Let's do a little example. So the measure of one angle in, say, a 12-gon, so a dodecagon, one with 12 sides, is, well, it's going to be 12 minus 2 times 180. We know what that is. That's 1800 divided by the number of sides. So that's 1,800 degrees divided by 12. And you can check it if you like. That is indeed 150 degrees. And in fact, you can do a little experimentation. But as you go up in sides, this is a regular 3-gon or triangle, and its angle measure is 60 degrees. A square has an angle measure of 90 degrees. A pentagon, you can check, has an angle measure of 108 degrees, and you can keep going, and you can check that as you go up in the number of sides, then the angle here increases, but it doesn't increase without bound. In fact, if you think about it, it's going to get closer and closer to 180 degrees, because 180 is a straight angle. But for any polygon, well, there's a bend to get it kind of back towards the direction that it came from so that it can close off. So you can't have it go off forever. It needs to bend, and so the angle has to be less than 180. But as n grows, then the angle gets closer and closer to 180 degrees. And let's do one more example. Is there a regular N-Gon with angle measure (135 degrees). So, again, pause the video now, see if you can use that formula that we just developed to check if this is possible. Remember, n has to be a whole number, and it has to be 3 or greater. Okay, now that you're back, let's do this. So remember that the angle measure of a single angle inside of a regular N-Gon, since all of the sum of the angles have to be divided evenly, since every angle is congruent. That is n minus 2 times 180 over. So now we have a little bit of a problem to solve, an equation to solve. So what we can do, we want to solve for n. Let's multiply both sides by n. N's not going to be 0. You can't have 0 sides, so we know that dividing by n isn't going to screw things up. So let's multiply both sides by n. And we get 135n equals n minus 2 times 180. Let's expand the right-hand side out. 135n equals 180n minus 360. All right, let's bring over the n's to the left-hand side and leave the constants on the right. So let's subtract 180n from both sides. And 180 minus 135 is indeed 45n, and 180 is the bigger number, so we'll keep that sign. So it's negative 45n equals negative 360. Divide both sides by that coefficient. And you can check, if you like, that 360 divided by 45, remember, we have a negative divided by a negative, so our answer is going to be positive. 360 divided by 45 is indeed 8, so n is 8. So in fact, we do have a whole number that's 3 or greater, so there is a regular N-Gon with an angle measure of 135 degrees, so yes, there is. It is a regular octagon. So now you can get a feel for how sums of angles and polygons work, and regular polygons as well.